Hi, my name is Alex, and today we're going to be taking a look at the lighting obstruction models that are new with STK12. So here I have a scenario, and it's set at a location that you might find familiar if you've done any of our certification training, which I encourage you to do. So here is Mount St. Helens. Here I'm just using the AGI terrain server, and I've added a place object that is directly in the crater that defines Mount St. Helens. It's a pretty simple scenario, but what I want to do is go to my place properties and just show you in this basic position tab there's this new feature, this new option called lighting obstruction model. And there are 4 options for this lighting obstruction model. There's Azel Mask, central body shape, ground model, and terrain. And each of these calculate lighting for your object in a different way. And what I want to do is kind of describe those different methods of calculating lighting. So the first thing I want to show you is the central body shape model. So it's right under Azel Mask, and what that does is it uses the explanatory supplement to the Astronomical Almanac, or the ESAA. It uses that method of calculating the body's local radius and then using that for obstruction. So basically you're taking a circular sun and a near-circular planet based on the radius of wherever your object is and using that to calculate lighting. So it's not particularly accurate, it doesn't really take terrain into account, but it does do general lighting, and if you're not really worried about it, doesn't make a huge difference. The next option that I want to go over is ground model. So what the ground model does is it changes the local radius based on where the object is. So this is a bit more consistent because you're using the terrain a little bit. You're using the altitude, and instead of using the ellipsoid of the Earth, you're using the ellipsoid of where this object is. So it's going to be more consistent, maybe a little bit more computationally intense, but overall, if you really care a little bit about lighting, ground model is going to be better than central body. The next option I wanted to go over is terrain. So terrain's a pretty good option. So terrain takes your object and takes the terrain around it and models those as ellipsoids. Similar to the first option, the central body option, it'll make these round ellipsoids based on the terrain around your object, providing that obstruction. And so instead of using just the Earth, the body, or whatever body you're looking at, it's using the terrain and simulating that as other ellipsoids. So while you're not going to get the most perfect demonstration of jagged outcroppings around your object and lighting coming through in the form of a shadow and having a really accurate report down to the second maybe, you're going to get a really great estimate of how much lighting your object's getting, especially if it's in a hilly area or something that's not particularly mountainous but a bit flat. In Mount St. Helens, this would work really well. The fourth option here is Azel Mask. And so azimuth elevation masks, if you've used SDK before, I'm sure you're familiar. Azel masks basically send out rays from your object in every direction and determine where there's obstruction. So this is normally used for computing access, but in this case it's being used for computing lighting. And what's happening is ellipsoids are being made around that Azel mask. So Azel mask can be fairly accurate as long as your sampling size is small enough. And that's more of an Azel mask setting than it is a lighting obstruction model, but it can be a fairly accurate way to compute lighting as long as your sampling size is small enough, and again, you don't have too many rocky outcroppings, things that will really create a sharp difference in lighting. Now that I've kind of gone over those 4 options, I'm just going to set the terrain option because it's my favorite. I think it's usually the most accurate and the most consistent for most uses. I'm going to set it to terrain. I'm just going to hit OK. Going to accept those changes. Now I'm going to look at my 3D objects window, and I'm just going to hit play, and I'm going to watch this shadow come across Mount St. Helens. So the shadow, this graphic, will be there regardless of what option you're choosing for your lighting obstruction model. However, it won't be computed as such unless you're using something like terrain. And so in this case, I'm using this terrain option, and what I'm seeing on the screen, this shadow as the sun rises and sets, this is what I'm going to get in my report because I'm using the terrain option. So if I click on my place object, I go to the report and graph manager, and then I have lighting times here, but this is an installed style. So I'm just going to generate this lighting times report, and it's going to give me a breakdown of sunlight times. So penumbra times, umbra times, so umbra is complete darkness, penumbra is partial darkness. And then sunlight times is when I have direct sunlight. And you'll see that I'm getting these numbers that match almost exactly when the shadow is crossing over my object. So if I set the scenario time to this date here, when I'm supposed to have sunlight, you'll see that I do in fact have sunlight, which is what I expected. If I wanted to see when I have darkness here, I wanted to go to Umbra, so I can go to this start time. And again, there's a shadow right over my place object. And this is a pretty complex shadow. As you can see, part of the crater is lit, but because I'm using that terrain lighting obstruction model, it's recognizing that there's darkness over my place object. So this could be a great option for getting an estimate of how much lighting you're going to get a location. If you're using solar panels for something, if you think that sunlight's going to interact with your communications, this is a great way to see how much sunlight you're going to get. Thanks for watching.